We are starting with Fei Teng from Penn State, talking about color kinematics, duality, and color spacetime background. Please.
And thank you for the introduction, and thanks a lot for giving me the opportunity to present my work in this wonderful conference. So today I'm going to present a my talk will be based on two works. One is, do you see my cursor?
Yes.
Okay, great. So one is a paper published earlier this year with Pranav, a student at Penn State, Aiden, a student at Michigan, and Radu at Penn State, and also a work in progress that we expect to finish around the new year. So our motivation is to see if anything that the wonderful technologies we learned by flat space amplitude can be actually used to explore the ADS boundary correlators and also the theta boundary correlators. That is our motivation. So we can learn a lot of physics in curved background. For ADS, of course, we have the well-known ADS CFT correspondence. So any new knowledge about the scattering in the bulk can actually tell us something new for the boundary CFT. And then for the theta, we have a different boundary. It is a open conformal boundary. And unlike the ADS, you have a closed conformal boundary. Then the correlator here, they are actually more relevant to to cosmology, to the observation of CMB. They are called cosmological correlators, and they probe the early history, the inflation phase of our universe. And a lot of interesting features of the cosmological correlators have been covered by the talk yesterday by Guilherme. And finally, we have the ADS, we can consider it as a regulator for the IR divergence in scattering amplitudes, and there are ways to reconstruct and study the IR feature from the ADS correlators. So an immediate question one might ask after seeing the motivation is that, well, we know that ADS is very, very different from the flat space-time. Here is a metric in the Poincare patch, and I will be using this patch, mainly use this patch in my talk. So a very distinct feature is that if even if we just consider tree-level scattering in ADS, we draw tree-level Witten diagrams, and we know that already at tree level, these Witten diagrams will evaluate to lead to rather than some rational functions, unlike flat space amplitudes. So is there can we actually draw an analogy between Witten diagram and flat space amplitudes? In fact, it is possible. So there are some very interesting recent works on exploring how to define and utilize the unitarity methods in the bulk, like defining what do we mean by a cut or a factorization, etc. So our question here is, we know that it is possible to define some properties similar to flat space amplitudes. Is that possible? Actually, we rewrite the correlators in such a way that we don't need to sweater to see these nice properties like unitarity factorization. Can they be manifest in a way very similar to flat space amplitudes? And something more, which is that we know there are color-kinematics duality and the double copy constructions for flat space amplitudes. Then is it possible to also do it on top of the ADS correlators? With these questions, I think for anyone who have actually listened to Zvi's talk during amplitude this year, we know for us the best approach is actually to get our hands dirty, dive in, do some explicit computations, stare at the results, and see if there are any structures. If there are any structures, then is there a way to systemize it and apply to more general quantities? And so then we derive new methods and new computations that manifest some hidden structures in the object we are interested in. So with that, we should just dive in and let the results talk. So then I will first, actually many people are following that route. They are doing computations to see if the properties I mentioned hold in ADS correlators. So usually there are different representations we can work we can write ADS correlators. If you open any like ADS CFT textbook, you start with position space, you solve equation of motion, and you solve 2-point functions in the position space. You can also go to the momentum space, because if you look at the direction parallel to the boundary, it is still you can still have conserved like a momentum. So it is of course there is some subtlety regarding the radial direction, the z direction, but you can still do the work in momentum space. Finally, there is another choice. It's quite recent, although it's already more than 10-year-old, the Berlin space approach. So in fact, I will start with the Berlin space, because there is a recent, very interesting results that that actually work. I mean, the color kinematics and the double copy actually work. So this is the if we are considering a scalar correlator, we can do a Berlin transform from the position space to the space of Berlin variables. Here, the delta ij, they are integrated under certain constraints, and you can trivialize the constraints by introducing n times n minus 3 over 2 normal Mandelstam variables. They satisfy the normal momentum conservation relations, and actually it's for a massive kinematics. So in these two papers, like these people, they looked at a boundary correlator that constructed from an n equal to 2 constructed from an n equal to 2 super Young-Mills. More specifically, they look at the super conformal primary operators, which are typically symmetric single choice operators in the symmetrized in the R symmetry indices. And what they find is that if you prepare these boundary states and let them interact in the bulk by exchange gauge boson gluons, then you actually see color kinematics duality work as if it just like the flat space. And if you double copy that, you will get an n equal to 4 super you will get correlates of n equal to 4 super conformal primary operators. In the bulk language, they would correspond to scalars in the type 2b supergravity on ADS5 times S5. There is a small twist though. These things, they don't work for Berlin amplitudes, but it works for something called a reduced amplitudes. Since you can, due to the superconformal symmetry, you can always pull out a universal piece which is fixed completed by conformal superconformal symmetry. So this 2 means that I'm considering n equal to 2, and after that you see the nice properties. If you don't do that, then this factor, which will become an operator in the Berlin space, is going to mess up the pole structure, and it becomes obscure. So this procedure is this factor you can understand it or like as an ADS analog of the delta Q tilde if we write amplitudes in a non-chiral superspace. And because we are working in a non-chiral superspace, and if you actually look at this paper and look at these numerators are non-local. It's just a normal usual statement that if you are in the non-chiral superspace, you cannot manifest a supersymmetry and a locality at the same time. So next, I'm going to move to the momentum space. In fact, the momentum space is the most phenomenologically relevant computation, because for cosmological correlators, we write it in momentum space, and they immediately feed into the equation for cosmological evolution that computes like the large scale structure and even the CFB radiation nowadays. So we can go to momentum space, and the momentum along the boundary dimension is the usual momentum. They are conserved, but because there is no translation symmetry in z direction, so if we write down a null momentum, then the z component is not going to be conserved, and we define a variable called total energy. They are typically not 0, and we can also define something like a Mandelstam variable S tilde, and then the S plus T plus U will become will be proportional to the total energy. In the flat space limit, you actually need to analytically continue this E total energy to 0. And this way, then this S tilde, T tilde, U tilde, they reduce to the normal flat space S, T, and the U. And the correlator in this limit, it is singular, but the residue at equal to 0 give you back directly the flat space amplitudes in the momentum space, just what we are very familiar with. So there are a bunch of nice results derived in 4D. So as in ADS4, both ADS4 and the DS4 for cosmological correlators, which we have heard yesterday, and some ADS correlators. Like in ADS, like I think it's the last one, the Durham group. They computed like helicity amplitudes in ADS background, and there are like they show that actually in ADS you can have all plus and 1 minus. There are these correlators. They are non-zero, but of course, since these correlators won't develop a pole when E goes to 0, so they vanish in the massless limit. In the flat space limit, and also the color kinematic duality hold like these that as usual. But here, but in terms of these S2, the T2, the U2, the variables, but because these variables they are not conserved, so in the amplitude language, the propagator matrix constructed from these Mandelstam variables they have 4 rank. So you can invert it, and the consequence is that you don't have the normal BCJ amplitude relations for these color ordered or correlators. So you can show that if you do that, they're proportional to a gauge invariant contact quantity, and this quantity, of course, goes to 0 when you take the flat space limit. So finally, you can do double copy, and there are working examples at 3 points. So finally, like I mean, in fact, I should talk about position space. And in fact, for us, our work we predominantly use position space. But I kind of wanted to rebrand that as an differential operator based formalism, because what we want is that what we want to show is that we can write a color dressed operator this way that basically draw analogy to flat space amplitude. You have the normal color factors, and then we can in fact replace flat space momentum by conformal generators, and as we will see very shortly, this is kind of the best analog to flat space on-shell kinematics. And now the numerators will become operators acting on a D function. The D function is nothing but a contact diagram in the bulk, the trivial contact diagram in the bulk. Since now, although the kinematics are almost the same as flat space, but now it is the kinematics, these identities are given in terms of Dij operators. So then you have subtleties related to non-commutativity, and it will affect double copy at the end. But like but anyway, like there are very interesting worldsheet formalisms that directly land you onto this form, and the worldsheet formalism, of course, resembles what we resemble the CHY, but the target space is no longer the momentum or momentum twister, but it will become these operators. So there are you can do that. You can construct a worldsheet formalism for phi cube in generic dimension, and you can do this for ADS3, Young-Mills plus Chen-Simons. And there is another work which did that for phi-4 indirection on the theta background. They are using a momentum space, but again, since if you write everything in terms of operators, it's quite agnostic to what representation you use actually for this D function. Then in the work we put out early this year, we show that it is possible to find a color kinematic duality, and we find this explicitly for nonlinear single model at 4 point and 6 point, and we believe that this holds generically for arbitrary higher points, and all you need to do is literally just replace momentum p by conformal generators in the flat space BCG numerators, and then it is automatic that knowing having color kinematics, you can derive BCG amplitude relations on color ordered operators or correlators. But now instead of multiplying Mandelstam variables, it becomes a differential relation. So it is D12 and D13. They are conformal generators acting on the correlators. And we worked it out for NLSM at 4.5 at 6 point. And we work it out also, we check that this relation holds for Young-Mills in D equal to 4 and also D equal to 6. And find an advertisement. So you will see tonight that one of my wonderful collaborator, Aidan, he will put out a paper on how to use this operator formalism to study certain one loop correlators. And finally, how to do double copy. This is a very good question, and there are subtleties related to non-commutativity, because in this formula, if you want to squeeze in another numerator, there are multiple places you want to put it, and they are inequivalent. So I will touch that at the end of my talk, but I just want to mention that there is there's kind of some working examples. Like this paper shows that in D equal to 3, and also at 4 points, you can double copy NLSM into special Galilean. Note that this special Galilean is not just an minimal uplift of flat-based Galilean, you just put it into the curved background. It is special in the sense that it should also have enhanced shift symmetry. So it is the Lagrangian, even on the curved background, should have that feature. So let's just do some, go for some, look at some, just some the formalism of position space, because that is, we are going to use many on differential operators, but we write these differential operators more explicitly in position space. So in more specifically, we use embedding space. Namely, we put the ADS, we realize ADS as a hypersurface in the flat space, one dimension higher as an hyperboloid. And you can show that this map, this embedding, produce you the Poincare patch, the metric I shown like here. So, and for a point on the boundary, you can take z goes to 0, and you perform a local conformal transformation. Then you find that a point on the boundary locates on the light cone in this embedding space. Then finally, if you are considering spinning correlators, then you will need polarizations. Then polarization can be also encoded this way, and it has to satisfy the transversality condition. It should be transverse to the ADS hypersurface. So then in this embedding space, the benefit is that you can write the conformal generators linearly. It is a linear operator. In fact, it is just the Lorentz generator in the embedding space. And the momentum conservation now becomes the conformal word identity. Namely, you act this Lorentz generator onto a conformal partial wave or a correlator, you get 0. So this is the momentum conservation. You can define similarly a Mandelstam variable in terms of operators, and they satisfy similar relations as Mandelstam variables. And this conformal word identity hold when you have on a support, like in flat space, momentum conservation hold on a overall delta function. So for correlators, it holds when you always have such a D function, such a contact diagrams. And here it is just a integral over bulk to boundary propagators, and you integrate it over the entire ADS. Finally, like for massless, so the mass of an unshelled particle, it becomes, or you should replace it by eigenvalues of the quadratic Casimir operator of this built from this D. Note that this mass is not the mass you use in the Lagrangian, in the bulk Lagrangian, or the one appear in the equation motion, but this is just an invariant quantity belonging to a boundary state. So now the non-commutativity here, since they are operators, they don't commute. But if we show that these operators, if they are associated with internal lines of a Witten diagram, they always commute. And in fact, this paper nicely shown that the inverse of these operators can be understood as bulk-to-bulk propagators. I'm not going to derive that, but I will give you a more generic derivation, but more formal one for a generic spin S exchange. So this works for scalar exchange. So I'm not talking about a generic spin S exchange in the bulk. So I just formally write like this line. So I have a current, a vertex function, another vertex function, and then a circle means that they are contracted with a bulk-to-bulk propagator in a meaningful way. Then we know that bulk-to-bulk propagator is an inverse of equation motion acting on a delta function. Then then the double integral becomes a single integral, and then you have this 1 over the inverse of equation motion. Finally, we can show that the equation motion, when act on a current J, the action is in fact equivalent to the action of D34, the one the conformal generator acting on boundary state. So we can do the replacement and pull out the operator, and then it's interesting to see that you kind of develop a quote unquote a pole in the operator space. It's not well defined, but it looks like a pole. The pole happens exactly when your internal particle kind of going on shell. So this is the eigenvalue of the quadratic Casimir. So if you remember something from yesterday's talk by Guilherme, then if you want to solve this diagram, well, you can have an he uses an differential equation. So here it is also a differential equation. You just move this operator to the left hand side, and on the right hand side you have a contact diagram and contact interaction. Then you solve the differential equation. But as I will show later, for our case, the differential equation is actually can be solved rather trivially. Like you don't even need to know that it is a differential equation. So then explicit result for a gluon and the graviton exchange, we have the bulk propagate in this representation look really like just a flat space one, like you get from Lorentz gauge. It just becomes an eta AB, but now since it's in embedding space, you need to project properly to ADS hypersurface, and you have the donor gauge graviton propagator, and you have the correct effect because the bulk is now D plus 1 dimension, so D minus 1 is D plus 1 minus 2. And in principle, our this approach can be applied to generic spin S gauge bosons, which has that conformal weight. And schematically, the result should look like this way, and you will have a non-trivial numerator that is a kind of a linear combination of various projectors. So now, once you are in this form, the bulk integration will be rather trivial, and the result it will be, well, I mean, you can write down the result without even thinking. So let's say we are looking at the gluon exchange. We start with a very reasonable Lagrangian. We have two flavors of scalars, and we have the minimal coupling to the gluon, and then we have an 5-4 coupling. And if you compute the S-channel Witten diagram that way, then it's just what you expect from flat space amplitude. You literally just replace all the Sij by the operator Dij. And you can show that if you compute all the diagrams, the Jacobi identity for numerator, they just trivially satisfy. So here, the first line is for the correlator of 4 identical scalars. And the second line, it is for distinct flavor scalars. Note that if they have distinct flavor, then the gluon exchange is only allowed in S channel. The T and the U channel, they are contact diagrams. They are contributed by these contact diagrams. And here I just fake a propagator and then I get a numerator. So finally, then you can also easily show that with this expression, the differential BCJ relation is, they just hold. You can do the same exercise for graviton exchange. We know that this is the Lagrangian that come from the double copy of this Lagrangian, the gauge Lagrangian. It is just the minimal coupling of 2 distinct scalars. And if you compute the Witten diagram, then we know that the quadratic Casimir of a graviton, it is not 0. It is actually equals to 2D. And if you are naive and just say, okay, let's just look at the flat space result and replace all the Sij by Dij, then you will miss this 2D. But I will show later that even if you made that mistake, at the end, physics is going to save you. The formula is smart enough that it can tell you that you made a mistake by its own. So, but of course, having this 2D, it can mess around with the double copy. But nevertheless, both the correlators with 4 identical scalar and the distinct flavor scalars can be obtained from a universal or a unified prescription. Like you just do a shift correspondingly in the numerator. And since this 2D, if you bring in the ADS radius, then in the flat space limit, since this is inversely proportional to radius square, then this shift goes to 0 and you reproduce the flat space result. And of course, like this prescription, whether it is like sensible or not, we need to look at higher point examples like 6 points. So now here is a question. these representations, they look really nice, really neat. You can get it with no effort if you know flat space amplitudes. But if you are, but some experimentalists come approach you and say, I want a number. How are you going to crank out a number from these expressions? Of course, you can just undo whatever I have done and go back to the beginning. Then there are tons of literatures on how to evaluate these diagrams in the past 20 years. But that defeats the purpose of what I'm doing here. Like, then why do you, then this like rewriting is meaningless. But what I'm going to show later in the following is that I can get a kind of crank number out, or at least do as good as what conventional method can do by only knowing how the Dij acts on D functions. For example, this thing, and when I write Pij, it means the dot product. So
5 minutes, including questions. So if you can wrap up soon.
Okay. Yes, I have 2 more slides, and yep. So here, this is the example of how this can be done for a scalar exchange. You just apply this operator onto this quantity, and then once you do that, you move the operator to the right hand side. What you see is a recursive relation for the quantity in blue, and this recursion goes to deep and deep. It goes deep when k this power goes more and more negative. But somehow the prefect says that if the combination is an integer, then this recursion terminates. Then immediately you get this result, like you write it in terms of a expansion of D functions. This of course agrees with the famous result by Dr. Freeman and Rastali. In their paper, they say like they derive this result without really trying, but they have to solve differential equations, changing variables like in a very mysterious way. But I will say like this approach, it's really straightforward and it's really without really trying, since you don't really even need to know that this is an integral. And you can do the same thing to work out the Gluon and the graviton exchange. Like here, I just gave example that I'm considering massless scalar correlators in even dimensions, just as such that the expansion in D function, they truncate. So similarly, you just start with this quantity, this operator, this operation, you draw a you derive a recursion and then you solve it, you get that. And for graviton, it's the same thing, you get the result. And as I said, if you forget this 2D, then you will see that the prefect is not going to factorize, and this recursion is not going to end. And you know by a fact that this correlator should have a finite expansion in terms of D function, even dimension. And then it really begging you to put this 2D back in this combination. And we believe that this of course should work for high speed exchange. All you need to know is like you just start with that and you build a recursion. And as I said, like expecting that they have finite sum in even D almost fixes the correlator. Like if you made any mistake or you forget 1 or 2 terms in the starting point, you just cannot make recursion terminate. So this is a summary of what we have done, and we basically construct the differential representation for scalar correlators, and we find that there are nice CK duality, and then there might be a double copy form of prescription. And then finally, like we have this derivation of D function expansion completely in terms of operator algebra. And I think I can stop here with like some possible future direction. One thing I want to mention like explicitly is that in this new formulation, you can get like it is possible to, or it is sensible. It is interesting if we can find a sensible definition of pole residue factorization. That is what I mean. Like if we can write it, we can define this quantity in a manifest way. Like maybe we need something like non-commutative geometry. I don't know, but I think I will just stop here.
So let's start with questions here. The audience. Any questions? Okay, so questions on Zoom.
Okay, can I ask? So about graviton exchange and gauge fields, do you see a way to double copy the whole thing, or your approach will work diagram by diagram?
By hosting, do you mean a kind of a KLT-like double copy?
Like taking the whole Yang-Mills 4-point function, double copy into the 4-point function of GR.
Oh, okay. So that is related to what we are like. So what we know is that Yang-Mills correlator, they satisfy color kinematic duality, but in a weaker way. So this weaker way, like it's not in terms of operators, STU, but it's in terms of like the action, the number after you acting the operator on the D function. This still guarantees you the differential BCJ relation, but now like if it's just this number, you don't know how to do double copy. But for scalar correlators with Yang-Mills, with Gluon and graviton exchange, then I think this is the usual way to kind of double copy the whole thing. But what we don't have, this is kind of what we usually call a BCJ type double copy. You do it diagram by diagram. I mean, I'm double copying all the diagrams. But what is more obscure to get is kind of a KLT like double copy because now you have, it's again related to the non-commutativity of operators. Like there will be ambiguity related to how you're ordering these operators. And if you order it in a wrong way, you will get a different theory.
But do you think that the ordering ambiguities will give you different theories, but all sensible? I mean, could it be that the difference in the ambiguity is just generating like irrelevant context terms from like higher derivative theories, or?
Yes, it's possible. So there are examples like if like that. So we know like here, like I say, like if you double copy scalar correlators with Gluon exchange, you use the first line. But somehow, if you want to double copy scalar Yang-Mills with an NLSM, suppose you should get a dBi scalar correlator. It's written this way. But if you get the correct result only when you double copy it in a different order, you put 1 over dij in middle. If you do it differently, then you will get like additional contact term, and you might get additional particles getting exchanged in between because you are not going to cancel this propagator explicitly. There will be an exchange channel.
All right, I see. Thanks.
And by the way, just let me say that we have created a Slack channel. So if there are any questions, we can just go and discuss in Slack.
Yes, please join the Slack channel. Any more questions here in the audience or on Zoom? If not, thanks, Peter, again.